If you think about an exponential equation, it's something in the form y equals b to the power of x, where x is a variable that's up in the exponent. So, thinking back to when we learned about inverse functions, remember we used the switch and solve strategy. Well, if we switch and solve y equals b to the power of x, it would become x equals b to the power of y, and we would need to solve this for y. But we don't have a method for solving for something that's in the exponent, so what we do is we define a new function, and we say that y is equal to log base b of x. So a little bit of terminology. So notice this b is the base. It was also the base here as well. So the exponential has a base and the log has a base. Y was the exponent, and so this y is the exponent. So a log is equal to the exponent that you would need. The last piece, this x, when we're talking about a log equation or a log function, we usually refer to this as the argument. So the argument is just when you have a function, it's what's going into the function, any kind of function. So here we have a log function. So we have a log base b of x, and that gives us this exponent of y. So this, what we had after we did our switch and solve in this log equation, these are equivalent to one another, meaning that they mean the same thing, they're just written in two different ways. So looking at x equals b to the power of y, and y equals log base b of x. So notice we'll usually write that argument inside of parentheses just to make it clear. That's also how we'll type it in our MyOpenMath expression. So I'm going to rewrite this in the reverse direction just so that you can see a rewriting strategy. So if we have log base b of x is equal to y. To see how to switch back and forth between these two ways of writing this equation, one of my students one time gave this the name the snail method. So that sounds kind of silly, but here's why she called it the snail method. So if you have log base b of x equals y, to turn it back into the equation that's written with an exponent, we take b to the power of y and set that equal to x. And so it kind of makes a swirl as we think about that relationship that b to the power of y is equal to x. So she said she thought that this looked like a little snail, and that was its curlicue shell. So if that helps you remember how to do the rewriting, feel free to use that for sure. So when you have log base b of x equals y, so the way that we're doing that rewriting is we take this base b and raise it to this power y and then set it equal to our base of x. That will give us a way to rewrite from the log form to our exponential form. So a couple other notes about logs as we're working here. There are two types of logs that show up most frequently as we're working. There's one that is called a common log, and this was a log with a base 10. And then there is also what is called a natural log, and this is a log with a base of e. Because these two logs get used most often, we usually use kind of a shortcut notation for writing them. So when you see something written just as log of x and there is no base written in, just an argument, then this is when we're assuming that our base is 10. And when you see natural log ln written with an argument of x but no base written in, we're assuming that's a base of e. And so the common log is when we have a base of 10, a natural log is when we have a base of e. So looking just at one example here to finish things out. So if you were to see something like log of 1000 and you were trying to find the value of that, we could think of this as log base 10 of 1000, since this is a common log, since no base was written in. And so we're trying to find out what the value is for that. So use that snail method idea to help you think through. This is saying 10 raised to what exponent will give you 1,000. So 10 to what power is equal to 1,000? Well, we know that 10 to the third power is equal to 1,000. So this means that log of 1,000 is equal to 3. So a log is equal to the exponent that you would need on the given base.